You're listening to a podcast from 702 and Cape Talk.
It's 10:07 and I am the stand-in, Mark Solms. I'll be receiving your calls from 10:30, but now we have our regular Naked Scientist slot. And Chris Smith's going to be talking to us. Remember, you can call in during that slot too. The numbers are 021-446-0567 or 011-883-0702. You can also text us on 31702 or 31567. Hi, Chris. What are you going to be talking to us about today?
Oh, good morning, Mike. Well, something that caught my eye is actually a revolution in data storage, potentially. Now, tech-savvy listeners will remember 25 years ago, IBM made history when they published on the front of a magazine the letters IBM written with a handful of atoms of xenon. And everyone said, this is the future, because people are literally moving and visualizing atoms one at a time. But 25 years later, we're actually potentially going to see a spin-off of this. A group of researchers who are actually based at Delft University of Technology in the Netherlands. This is a group who are publishing in Nature Nanotechnology this week, Sundar Orta and his colleagues. What they've managed to do is to come up with a system that uses atoms to store information, and store information with thousands of times greater density than the best hard disks that we have at the moment. And this is important because around the world, every day, we're generating about 2.5 million terabytes of data. And the problem is not the data creation anymore, it's the data storage. And big projects like the Square Kilometre Array coming to South Africa and Southern Africa and Australia towards the end of the decade, that's going to generate more data about the sky and space in a day than the entire world generates in a year at the moment. So where are we going to put it all? This new approach that this Dutch group have come up with involves depositing atoms of chlorine on a small sheet of copper. And rather than have the copper surface completely filled with chlorine atoms, you leave some gaps. You then use a scanning tunneling electron microscope to put an electric current in where the chlorine atoms are, and you can move them around. Rather like, if you remember, an abacus that you probably had at school where you move beads around to store information or do sums. You can do the same thing with chlorine atoms on this copper surface. And they can write data into it by pushing the chlorine atoms around in certain positions, and then using the same microscope to read where the chlorine atoms are. They say it will store 500 terabits per square inch, which is thousands of times denser than hard disks that we have at the moment. The only downside to the present technology that they come up with is, there are a couple of them, it works at minus 200 degrees centigrade, which is something of a challenge. It also is very slow. To read 1 kilobyte of data takes an hour. To write 1 kilobyte of data takes 3 hours. So it's not at the moment optimized, you might say, but it's certainly the first time anyone's ever managed to do anything like this and do it in a way that means you can actually change, write, and edit the data that you're writing and do it at enormously high density. So it's very exciting. This is possibly the future of how we can store information.
Gosh, densest data storage yet. My science is neuroscience, and of course we're all carrying around inside of our craniums an exquisitely attuned data storage device. So we have some callers are waiting for you. Ross is on the line from Thornton.
Yes, thanks. My question is quite a humble one, and in the face of the two academics who are on the other end of the line. I've wondered for many years why it is that warm-blooded animals, like a dog, for instance, it is always, when you think they're healthy, they have cold, wet noses. And if you have time, also, why do dogs wag their tails when they're happy, and it seems cats do it when they're about to pounce and when they're threatened?
Yes, absolutely. Well, why do dogs have wet noses? Well, they do lick their nose. They also need to lose heat, do it by panting and shedding vapour through their respiratory tract because they can't sweat in the same way that we humans can. So therefore, dogs' respiratory pathways are the major route out of the body of evaporating fluids to keep themselves cool. Also, their noses are very long, and as a result, they tend to have slightly different airflow in the nose to slow down the rate of how gases and chemicals move into the nose so they can detect chemicals more effectively. All of those respiratory surfaces are well supplied with blood, which means that they're adding water to those surfaces. And this is also to moisten the air that they breathe in. So there's a range of reasons why a dog's nose is going to look wet. When dogs wag their tails and cats flick their tails, these are very visual animals, and they have adapted this body part to send signals to each other. Dogs and cats are interesting in that they also work as teams. Dogs hunt in packs. You also see lions hunting in groups. If you're lucky enough to go on safari, go and watch them. And sometimes if you make a noise when you're stalking, you're going to give the game away. So by having visual signals where you don't have to make a noise, but you can actually show what your intentions are to your friends around you or potentially also your foes, then you have another route of transmission of information. You have a less ambiguous means of transmission of information, and you also have a way of stalking something without giving the game away, potentially. So I think there's a range of reasons why dogs and cats flick their tails and have evolved to use that signal, which is a visual one. They've got good eyesight, so why not?
So there you have it, Ross. Ask a clever question and you get a clever answer. Remember, we are taking your calls on 021 446 0567 or 011 883 0702. You can also text us on 31702 or 31567. Next up for you, Chris, is Willie in Randburg.
Morning, gents. Chris, I've sort of been thinking about the question for a while. If you've got a train moving in one direction and you've got let's say a small insect going along the same track but in the opposite direction, if these two bodies collide, in theory they become one at some point, and one of those bodies goes through a point of zero speed. So the acceleration obviously decelerates in the original direction of movement and then starts moving with the train. But if those two or if one of those bodies goes through a speed of zero, then in theory, both bodies, when they combine, should go through that speck of zero speed. But we know the train keeps on moving undeterred.
Right, so what's your question?
Willie, are you still there? What is your question for Chris?
So the question is there a point that the train, in theory the train slows down a little bit because it's gained, some mass in the process, but the small insect went through a point of zero speed, in theory, when it was connected to the train. So does the train go through an instantaneous moment of slowing down?
Hi, Willie. Well, the answer is no, it doesn't. What actually happens, the insect has momentum, which is mass times velocity, and the train has momentum, mass times velocity. And because of conservation of momentum, when two bodies join, then the resulting momentum is the sum of the two individual momenta. And the momentum of the fly moving in the opposite direction to the train is going to be negative with respect to the train. So you'll take the train momentum and subtract from it the fly momentum. The train momentum is going to be a very big number. The fly momentum is going to be a very small number. So the net result is you'll still have a positive momentum on the part of the train. Where, in practical terms, when the fly hits the windscreen of the train at the front, then there is compression of the atoms, or that there's an attempt to squeeze the atoms of the fly and the atoms of the window of the train, and this stores energy elastically in the electrons around those atoms and between those atoms, and there will therefore be a sort of squeezing of the windscreen and then a bringing back, a rebound of the atoms in the windscreen. But in other words, the energy is absorbed elastically. There's no evidence the train comes to a standstill even for a picosecond and then carries on again.
Thank you, Willie. So, Chris, the next question comes from Janine in the wonderfully named place that I won't ask you to repeat. It's Kloppiesjachte. And here's Janine.
Hello. I'd like to ask you, please, why do people's noses and ears grow larger and larger as they get older?
Hello, Janine. It is certainly true. Not in everyone's case does it happen so demonstrably, but in some people's cases it happens very, very obviously. And the most likely reason is because these structures don't have big, long bones in them. They have cartilage in them. There's a fibro and elastic cartilage model which has tissue strung around on it like a scaffolding. It's like putting a drape over a scaffold. And unlike your long bones in your legs, if we take your femur, for example, the way that grows, initially, the body, when you're a fetus, the body lays down a cartilage model of the bone, and then cells called osteoblasts move in and they start turning the cartilage into bony tissue, except in a region called the growth plate, where new cartilage is added inside the bone, and it works a bit like a jack under a car. It continually adds more cartilage to the bone, which extends the length of the bone, and more of these bone-forming cells then move into the new cartilage and continue to ossify it. And you continue to grow your bones in that way until the growth plate shrinks to zero and the two bony ends meet, and then you stop growing. In your ears, in your nose, and in certain other parts of the body, you do not have these growth plates. Instead, you have cartilage, and the cells that make the cartilage continue to turn over, albeit very slowly, during your lifetime, and lay down more tissue. You can add tissue to those body parts, but they do continue to grow, albeit very slowly, and they can get bigger. And in some people, they get dramatically bigger, and there is a condition called rhinophyma, where you get a very, very big nose. Thankfully, quite rare.
Keep the questions coming to The Naked Scientist on 011 883 0702 or 021 446 0567. It's 19 minutes past 10, and we're going to take a quick commercial break.
702 and Cape Talk.
The Naked Scientist.
To The Naked Scientist, Chris Smith. Chris, we have Patrick in Alberton waiting on the line for you. Patrick?
Thank you. Good morning. I just want to know why a poisonous snake that would kill, say, a hawk, a bird, when it doesn't bite it and the hawk kills the snake, it eats the snake. And I'm presuming and assuming that the bird is not immune from its poison. And the bird and the snake, I'm presuming it's got ducts full of poison in it. When it eats it, why doesn't the bird or any other animal that eats the snake, why doesn't it die from its poison?
Mark, I'm sorry, the phone line is really bad from Patrick. Can you just summarise the question for me in a couple of words?
Patrick was referring to birds of prey that eat poisonous snakes, and of course it doesn't apply only to birds of prey, but he's wondering why, when they eat the snake and therefore presumably they eat the poison sac, why does the predator not die?
Yeah, excellent question, this one. And the reason for this is, and the reason most of these venomous snakes and most venomous animals have very sharp fangs or teeth or stings, is because venom is usually a cocktail, a mixture of protein molecules that need to be injected into tissue or ideally into the bloodstream, and they then circulate in the bloodstream, attacking various structures on our cells to disable them. Usually they go for the nervous system, and they disable the way that the nervous system talks to target tissues, including muscles, and they have a paralyzing effect or a sedating effect. But because these things are proteins, this means they're made of building blocks called amino acids, and they're the same stuff that the Sunday joint that you have, or egg, or anything else that's made of protein, is made of. And if you were to eat these things, they would go into your stomach, and proteins can be very readily, in most cases, broken down by the acid and the enzymes and digestive juices in your stomach and intestine. So if you swallow these venom molecules, usually they're completely harmless because they'll be deactivated by your digestive juices, and they can't get to the tissues that they need to get to attack, like the nervous system. So that's why animals have evolved to have ways of getting them through the skin and not having to force you to eat them. So when animals eat poisonous creatures, unless those chemicals that are part of the venom system are not broken down by digestive juices, then most of the time they're not going to be harmed at all. There are some exceptions. If you look at cane toads in Australia, for example, they are covered in these warty structures that exude a very nasty toxin. It's called a pamiliotoxin. And animals that eat them can end up becoming poisoned because the toads have evolved, A, to taste nasty, and B, to make these toxins to deter animals via that route. And actually what a lot of animals that eat these toads are now evolving to do, it turns out, is to flip the animal over and eat the underside, which doesn't have these warty structures that make the toxins, so that they're not exposed in the same way. So it's almost like animals are evolving and changing their behaviour to make sure that they're not succumbing. But in the case of birds of prey, they're just not actually being bitten by the animals, usually, and the venom doesn't work when they eat it.
Very good, thank you. Mike in Pinelands, sorry to keep you waiting. You're on air.
Hi, Chris. I know we're out of time, so I'll be quick. Metformin is a drug that was, first of all, despised and has now become the best drug for diabetes type 2. But the latest information seems to suggest that metformin might also be a magical anti-aging drug. What are your views on this?
To be honest, I haven't seen, Mike, the evidence for its anti-aging effects. You're right about its anti-diabetic effects. Metformin is a drug which it was talked about in slightly kind of scathing terms when I was at medical school about 20 years ago. People used to say, and there is also metformin. Metformin increases the way we use glucose around the body, and it also makes you feel not terribly well if you have lots and lots of sugar intake. So it kind of helps people to regulate their diet as well. Exactly how it works, I'm not sure, and how it would work as an anti-aging compound, I'm not sure. But certainly if you have very poor control of sugar, then, and because you're diabetic, it will certainly, that's going to accelerate the aging of all tissues because it imposes biochemical stress. It means your immune system doesn't work very well, and it also modifies tissues by adding glucose molecules onto them, which has an aging effect. So if you have better control of your sugars, that's going to have an effect. But I'm not sure why it would have, per se, an anti-aging effect. I'd have to go and look that one up, I'm afraid, Mike. So if you can park that one with me, I'll see what I can do for you next time.
As it happens, we're moving from type 2 to type 1 diabetes with Lee in Tilbach. You're on air, Lee.
Good morning. I'd like to know, please, if we're any closer to reversing type 1 diabetes with stem cells. I'll listen on radio. Thank you.
Okay, well, let's distinguish between type 1 and type 2 diabetes. Type 1 diabetes is usually a phenomenon occurring in younger people. It's an immune condition where, for some reason, and possibly in response to a preceding infection, the immune system then mounts an attack on the beta cells in your pancreas, which make insulin, completely destroying those cells and rendering the person completely incapable of making any insulin. And insulin is the hormone that you need to get sugar out of the blood and into your tissue. Type 2 diabetes, on the other hand, is a condition of... is there someone there? Hello?
She's listening on the radio, Chris.
No, I could hear another conversation coming in that was putting me off. I'm sorry. And type 2 diabetes is a condition of usually associated with obesity, and so some people talk about a phenomenon of diabesity. And this is when you gain weight for some reason. The gain of weight renders the body resistant to your own insulin. So although you're making lots of insulin, it doesn't work properly, and in both cases, blood sugar levels climb. In both cases, giving insulin brings sugar levels down, and we know that is healthy, but it's extremely inconvenient, especially for people with type 1 diabetes who have to continuously monitor their blood sugar and then administer insulin to themselves. And because, as we heard about venoms, insulin is a protein in the same way that a venom is a protein, and so you have to inject it to make it work. It won't work via the oral route. And this spoils people's lives. And so we would very much like to come up with a way of replacing the pancreas. And scientists are working on this in a number of ways. The big problem to overcome is, why did the immune system attack the pancreas in the first place? Because even if we put a new pancreas with new cells into that person, they're going to still have the immune problem that caused the disease in the first place sitting there. So we've still got to solve the problem of the immune response before we can then put in a replacement pancreas or replacement cells. One way scientists are doing this is to put new insulin-producing cells in a protective matrix. So nutrients can get in, oxygen and blood supply can be delivered. Insulin can get out, but the immune cells can't get in to damage that tissue. So that's one way that scientists are doing it. And there is optimism that there will be an artificial pancreas within a very short time.
So, thank you very much, Chris Smith, the Naked Scientist. Gosh, I really learnt a lot. I'm not a replacement pancreas. I'm a replacement talk show host. It's 10:30.